Hello, and welcome to episode 1 of Chem with M. Fun fact, back when I was in college, I was a tutor and a TA, and I always wanted to start a video series called Chem with M. And now I get to. Thanks, coronavirus. All right, if you are watching this video, that means that last time I saw you, we did the lab on the gas laws in which you were changing like the volume of a gas and measuring the pressure, or you were changing the temperature of the gas and measuring the pressure. So we are going to then today take notes titled gas laws, which will kind of go over what we did in the lab as well. And we'll learn how to do math to predict new pressures, volumes, and temperatures as well. All right, let's go. Gas laws, all right? So our essential question, our purpose, or our goal today is to look at how pressure, volume, temperature, and moles of a gas all affect one another, because these are all properties of gases, and if one of these gets changed, the others will be changed or affected as well. So if I change the temperature, that's going to also have an effect on the volume and the pressure of a gas. Or if I change the volume of a gas, that's going to affect pressure and temperature as well. So we're going to look at all these different gas laws and why the gas laws are that way based on how particles behave, okay? So the first one is looking at the amount of gas or moles of gas versus pressure. Where should I put myself to not be in the way? Oh, well. Okay, and if you have your lab sheet out, this was part 2 of the lab. It's either part 1 or part 2 of the lab. It was where you were changing the amount of gas that you pulled into the syringe and then seeing how that affected the pressure, okay? I want to say this was part 2 of the lab. Okay, so this one's kind of self-explanatory. We know that pressure comes from the collisions of gas particles against the walls of the container. So if there are physically more gas particles in a container, more moles of gas in a container, simply by having more moles of gas in there, there's going to be more collisions because there are more particles there to collide with the walls of the container, okay? So if we just want to isolate the relationship between moles and pressure, that means that we are assuming that volume and temperature are held constant. So if volume is being held constant and temperature is being held constant, then we can say, well, more moles of gas will mean a greater pressure, okay, because there'd be more collisions. Fewer moles of gas would mean a lower pressure because there would be less collisions, okay? So here's a kind of just a quick, easy picture showing this. This sample of gas versus this sample of gas. They both have the same volume, they're in the same space, and they both have the same temperature, so they have the same kinetic energy, but this one right here just has fewer gas particles than this one over here on the right. So the one with more gas particles is just going to naturally have more collisions between the particles in the container, so this container right here would be greater in pressure than this one over here. So that is the moles versus pressure relationship, all right? Okay. Let's get into what is called Boyle's law then. This was part 1 of the lab then. This is where you drew in a set amount of gas and then you kept pushing it in and changing the volume to see how pressure is affected. This law is called Boyle's law. And we should have gotten this graph, or you did get this graph when you did this lab. As volume increases here, as you increase the volume, the pressure is decreasing, okay? So you should have gotten a graph that looks similar to this in lab. This is an inverse relationship. So pressure and volume are inversely proportional. And again, this is when temperature is constant, okay? So mathematically, here's what Boyle's law is mathematically. P1 times V1 equals P2 times V2. The ones just mean like initial. Initial pressure times initial volume is equal to whatever the final pressure is times the final volume. So P1 times V1 equals P2 times V2, all right? So inverse relationship, if one goes up, the other goes down. If one goes down, the other goes up. They're moving opposite each other, okay? So this is the law. This is the what. Remember, a law and a theory, like one is not better than the other. A law just says, here's what happens. So in all of these cases, we're going to look at what happens, and then we'll talk about, well, why does this happen? All right. So here's the law, inverse relationship. The why then just comes down to gas particle behavior. All right. So if we have less volume, if we have a smaller space, well, if we have a smaller space for particles to be in, they're going to end up just colliding and hitting against the walls of the container more often because they're in a smaller space, okay? So it's like showing this picture right here. We have a small space. Here are all the gas particles. They're going to collide just because they're in that area. If we were to increase the volume here, in this picture below here, now if we give the gas particles more space to move around, well, if they have more space to move around, they're just not going to hit the walls of the container as often. So in this one, there would be fewer collisions. And we know that fewer collisions means lower pressure, okay? So you can summarize this in your own words, however you want to understand it. I wrote that less volume or less space means that gas particles collide more frequently, which would mean greater pressure then. More volume or more space means that they're going to collide with the walls container less frequently, so fewer collisions means less pressure, okay? All right, let's do some math then. For all of these gas laws, we'll look at what the law is, why the law is that way, and then we'll do one math problem together. And the purpose here is you can predict then, or you can know, based on changing pressure or volume, I can predict what the new pressure or volume will be, okay? So let's read through this problem. A sample of hydrogen gas has a pressure of 1.15 atm and a volume of 8.80 liters. If the pressure is increased to 1.55 atm, what is the new volume? I'm actually going to type my answers when I go through these with you because, as you see, if I try writing it here, not neat, okay? This is going to drive me crazy and drive you crazy, okay? So we are going to use the law, P1V1 equals P2V2, but I'm not going to try to use this marker on here because that is a mess. So I'm going to type this with you guys. I just hid the tools. Here we go. Okay. Sorry, guys. Now, here we go. So when you're reading through a problem, just identify what variables is this relating. This is relating pressure and volume. So I'm just going to remind myself of Boyle's law. P1 times V1 equals P2 times V2. All right. Then I read what's given to me in the problem. A sample of hydrogen gas has a pressure of 1.15 atm, so that's the initial pressure of this gas, and a volume of 8.80 liters. That's the V1 of this gas. So we're given P1. That is 1.15 atm. And we're given V1. That is 8.80 liters. Now we're changing something. The pressure is increased to 1.55 atm. We want to know what is the new volume then. So we also know P2. The new pressure is 1.55 atm. Our question then is, what is V2? That's like our X, okay? So for all these problems, it's just going to be identifying your variables and plugging in and solving for the unknown. For all these gas laws, it does not matter like what unit you plug in pressure in, as long as they're in the same unit. So if P1 is an ATM, P2 must be an ATM. Or they could both be in torr, or they could both be in mmHg. As long as they're in the same unit, you're good. Same with volume. Both volumes have to be in the same unit. So they can both be in liters, or they could both be in milliliters. In this case, since V1 is in liters, when we solve for V2, it's going to come out in liters, okay? So now if we do our work here, I'll go over here, plug in P1, 1.15 atm times V1, 8.80 liters, is equal to P2, which we know, times V2, or if you want to plug in X instead because you're used to seeing it as X, go right ahead, okay? So I'll take this first one step by step so you can see every step in case you want to. On the left side, we have 1.15 times 8.80. If you have your calculator with you, you can follow along with me. That is 10.12. Again, wait till the very end to round if you are doing a step by step. Equals 1.55 times V2. So now to get V2 alone, we will divide both sides. Ooh, sorry guys. I don't know why that's happening. This is my first video, if you cannot tell. So 10.12 divided by 1.55 then means that V2, the final volume, is equal to, now I will round to 3 sig figs. If you forgot about the sig fig rules, remember in your final answer, you only keep as many sig figs as were given to you in all the other numbers, okay? So check if you get what I'm getting. You should get 6.53. And then the unit is liters, because since V1 was plugged in liters, V2 comes out in liters, all right? So here's our answer. The final volume is 6.53 liters. Always check before you move on that your answer makes sense, okay? So in this case, we started with a pressure of 1.15 atm, and the pressure increased to 1.55 atm, okay? So if the pressure increases, we should expect the volume to decrease, which it did. The initial volume was 8.80 liters, so it makes sense that the new volume went down. Now it's only 6.53 liters. So do your math, but then always just check, like, does my answer make sense? And yes, it does. All right. I don't know if we need to go through another example together. If you want to see this worked out example of Boyle's Law, you can check out the classwork tab where it says notes, gas laws with filled out examples. I have worked this one out for you as well if you want to see another example, okay? Let's move on to another law then. This one is Charles' Law. This law we did not collect data on in the lab that we did last time, okay? But what Charles' Law is it is describing the relationship between the variables volume and temperature. So if we're just isolating those two variables, that means that now pressure and amount of moles are constant. And volume and temperature have a directly proportional relationship, meaning that as one increases, the other increases as well. Or if one decreases, the other decreases with it, okay? So if we had done this one in lab, here's the graph we would have gotten. As we increase temperature here on the x-axis, we see that the volume increases as well. So this is a directly proportional relationship. Here is the math equation for Charles' Law. V1 divided by T1 is equal to V2 divided by T2, okay? Again, the ones mean the initial and the twos means after some change. So volume can still be in any unit for volume as long as V1 and V2 are in the same unit. But temperature must be plugged in Kelvin. You cannot plug in Celsius and you cannot plug in Fahrenheit, okay? Because if you remember, Kelvin is the absolute scale, because what temperature really is average kinetic energy or average energy of motion. And we know it is not possible to have negative motion, but it is possible to have negative degrees Celsius or negative degrees Fahrenheit. But you can't have negative motion. So you have to turn it into Kelvin first and then plug it in for T1 or T2, okay? So if you forgot the equation, there it is. If you are in degrees Celsius, you can add 273 to that to get into Kelvin. If you are starting in Fahrenheit, you have to turn it into Celsius first and then add the 273 to get into Kelvin, okay? So this is the what. This is the what goes on here. If temperature goes up, volume goes up. Temp goes down, volume goes down. All right, that's the what. The why then, again, all comes down to what the actual definition of temperature is. Temperature is average kinetic energy, energy of motion and movement. So if we just think about this, when the temperature is increasing, what that really means is the gas particles are gaining energy. They're gaining kinetic energy. They're going to be moving they're going to be moving more, is what I meant to say. They're going to be moving more, and they're going to be moving faster, okay? And if they're moving more, moving faster, they have enough energy to get farther away from each other and spread out more and take up more space. And if they're spreading out more and taking up more space, well, that's a bigger volume, okay? Versus if the temperature of a gas is decreased, really what that means is now the gas particles are losing kinetic energy. They don't have as much energy anymore to move quickly and move far away from each other, so they kind of have to like come together and contract a little bit. And then take up a smaller volume, a smaller space, okay? So you can summarize that if you want my words or if you want to summarize into your own words, it's all there on the screen. This picture is just showing if I have some gas particles here and I heat them up and raise their temperature, really what that's doing is giving them more energy to move around more and spread out and move quicker, and they'll push against this piston and increase their volume here, okay? And this balloon is showing the same thing. Balloon at 0 degrees, I take it outside to where it's 20 degrees Celsius, and now the volume would increase because the gas particles in the balloon have more energy to spread out into a bigger volume, all right? So let's do one math problem with this. We have a sample of oxygen gas. It is at a temperature of 25 degrees Celsius, and it has a volume of 3.89 liters. Those are our initial conditions, okay? If the temperature is decreased to 15 degrees Celsius, what is the new volume? So again, what I like to do first and foremost is just write out the equation that relates to this one being Charles' law, means I'm going to use V1 divided by T1 equals V2 divided by T2. I am given V1. V1 is 3.89 liters. And I'm given T1, all right? It's at a temperature of 25 degrees Celsius. Can I plug in Celsius into a gas law, though? No. So I'm going to turn that into Kelvin by adding 273 to it. So 25 plus 273 means that T1 is really 298 Kelvin. It says if the temperature is decreased, so I know T2, we're changing the temperature to 15 degrees Celsius, but again, I have to add 273 to this to get it into Kelvin. Oh, sorry guys, that doesn't make sense up there. That's 288 Kelvin then. And the question is, what is the new volume? So V2 is my question mark, or my X if you want to plug in X into an equation instead. This one I'm actually going to try to use the marker and write this out because I feel like we will make a mistake cross multiplying otherwise. Okay, so bear with me because it might be a little sloppy. So if we plug this in then, I'll use blue. V1 is 3.89 liters divided by T1, which is 298 Kelvin. This is equal to V2, which is our unknown. So if you want to plug in X instead, just plug in X instead. Divided by T2, which is 288 Kelvin. Again, all of these laws are just doing algebra. I'm trusting that you guys can do algebra correctly. So I don't really care if you, how you choose to solve the algebra problems as long as you're doing it accurately. I have found that most people like to cross multiply anytime they see a fraction equal to another fraction. So I'm going to cross multiply this one for us. So if we cross multiply, this cross then is 3.89 times 288, which if you plug it into your calculator is 1120.32. And you set that equal to the other cross, which is 298 times X, or just 298x. And now to get X all by itself, I will divide both sides by the 298. So 1120.32 divided by 298 means that X is equal to, if I round this to 3 sig figs, we should be getting 3.76. And what's the unit? Yes, liters, because V1 went in as liters, so V2 comes out in liters. Sorry that this is kind of sloppy. Our final answer is 3.76 liters for V2. Let's check. Does this make sense? Well, the initial temperature was 25, the final temperature was 15, so temperature is decreasing. So does it make sense that our volume is also decreasing from 3.89 to 3.76? Yes, it does, because if temperature goes down, volume goes down as well because the gas particles are losing kinetic energy, so they're not going to take up as much space anymore. So it makes sense. So that is Charles' law. If you want to see another example of Charles' law worked out, I have worked out this one in the notes on Google Classroom, okay? Okay, third law then. Gay-Lussac's law. This one you did do in lab last time I saw you, which was a long time ago. But you did do this one. It was part 3 of your lab. This is the one where you were increasing the temperature of the gas in that flask and then measuring what the pressure was based off of that. And your graph should have looked pretty similar to this one right here. As the temperature increases, the pressure increases. So temperature and pressure also have a directly proportional relationship. If one goes up, the other goes up. If one goes down, the other goes down. They move up and down together, okay? So the mathematical law for this looks almost identical to Charles' law, only now it's pressure and temperature instead of volume and temperature. So mathematically, this is P1 divided by T1 equals P2 divided by T2. P1 and P2 can be in any unit as long as they're the same unit. So they can be in torr, mmHg, ATM, whatever, but T still has to be in Kelvin, all right? All the time, T must be in Kelvin. So this is the what? Directly proportional relationship. The why then, and again, if we are just comparing pressure and temperature, this means that volume is constant. So the space that they are in is staying the same. Just break it down again to what these definitions are. If temperature is increasing, the gas particles have more kinetic energy, all right? They have more motion, they're going to be moving quicker, faster, and just more, okay? So if they're moving faster and quicker, they're just going to hit the walls of the container more often because they're moving faster, okay? And more collisions would mean greater pressure. Versus if the temperature is decreased, now they're not moving as fast, they're just not going to bonk into the walls of the container as often, and therefore there would be lower pressure then, all right? So what this picture is showing is, here we have a gas. This is a constant volume because it is like the space that they can't leave, okay? So this is constant volume. We have some gas particles, they're moving around in here. Remember, you can use arrows to show like general amount of energy of the particles. So these gases have some energy. If we heat them up and these gas particles gain kinetic energy, these longer arrows mean that they're moving faster. They have greater speeds now. And with greater speeds, they're going to hit the walls of the container more often and therefore have greater pressure. So that is the why behind the what of Gay-Lussac's law, okay? Let's do some math. Okay, here we go. We have a sample of helium gas, and it has a pressure of 1.35 atm and a temperature of 21.0 degrees Celsius. If the pressure of the sample is increased to 1.67 atm, what is the new temperature, okay? So if I'm reading through this problem, I recognize that, okay, this is the relationship between pressure and temperature. This is Gay-Lussac's law. So I will write down what the law is again. P1 divided by T1 is equal to P2 divided by T2. I know P1, we are at a pressure of 1.35 atm. And I know T1, we are told that it is at 21 degrees Celsius, but I cannot plug in Celsius, so I will do 21 plus 273. T1 is 294 Kelvin. We are increasing the pressure in this sample to 1.67 atm. And the question then is therefore, what's going to happen to the temperature? What will T2 be? Hey, before we solve this, let's make a prediction. If the pressure is increasing, we should expect the temperature to, yes, increase as well, because they have a directly proportional relationship, all right? So let's solve this. I'm going to do this again to show the cross multiplication. So again, sorry, it's going to be a little sloppy. What color should I use? Green. So P1, 1.35 atm divided by T1, 294 Kelvin, is equal to P2, 1.67 atm divided by T2, which is the unknown, so you can plug in X if you want. So again, we have a fraction equal to a fraction. If you like to cross multiply, cross multiply. So this cross right here is 1.35 times X is equal to the other cross here, 294 times 1.67, which is 490.98. Again, wait to round until the very end. Okay, and now to get X by itself, I divide both sides by 1.35. Those cancel out. So we get X is equal to then 490.98 divided by 1.35. Now we can round to our final 3 sig figs. We should get 364 4, and the unit is Kelvin, because T1 went in Kelvin, T2 comes out in Kelvin. You have to be in Kelvin when you're doing temperatures here, okay? So you will get your answers in Kelvin. You can keep them in Kelvin. If you want to convert them back to Celsius or Fahrenheit because that's more familiar to you, that's fine. If I want to go from Kelvin back to Celsius, I would just do 364 and now minus 273. So if you want it in Celsius, this would be 91 degrees Celsius. And if you then wanted to take this into Fahrenheit, that's okay. I don't really care what unit you go to as long as you have the right number with the correct unit, all right? So this is Gay-Lussac's law. And if we check, yes, our temperature did increase just like we predicted, which makes sense because they have a directly proportional relationship. So that is Gay-Lussac's law. If you want to see another example worked out, example 2 is worked out in the notes that are posted on Google Classroom, okay? Very last thing, thanks for hanging in there, guys. I know this has been a bit for the first day. The very last thing is basically, what if nothing is being held constant? If everything is changing, then I can't use Boyle's law or Charles' law or Gay-Lussac's law. We have the combined gas law, all right? And really, this combined gas law is the only thing you need to know because it encompasses all of the other laws. So if you know this one, you know them all. P1 times V1 divided by T1 equals P2 times V2 divided by T2, okay? If you know this one, you're good. So let's see an example in which multiple things are changing here. We have a sample of a gas, and it is at a pressure of 0.987 atm, a temperature of 28 degrees Celsius, and has a volume of 25.5 liters. So we were given all those initial conditions. We were given P1, that's a P. We were given T1, and we were given V1, all the initial conditions of this gas. The pressure is increased to 1.04. So we have a change in pressure. P2 is 1.04 atm. And the temperature is increased to 55.9 degrees Celsius. So now we're changing pressure and we're changing temperature. And based off of both of these changes, we want to know what is the new volume, what is V2, okay? So since nothing's being held constant here, we have to use the combined gas law. So before we do this, just kind of think a little bit. If it was just the pressure change here, if just the pressure was increasing, we would expect the final volume, V2, to be less, to decrease, right? Because as pressure increases, volume decreases, okay? However, the temperature is also increasing. If it was just a case of a temperature increasing, we would expect the final volume to go up because we know as temperature goes up, volume goes up. So the pressure and the temperature changes here are kind of working against each other. So we just got to do the math to see what does the new volume end up being if both of these things get changed, okay? So let's plug this all in. 0.987 times 25.5 divided by T1. T1 is 28 degrees Celsius, so do 28 plus 273. This is 301 Kelvin. So I put in 301 is equal to P2, 1.04, times V2, which is our unknown, so you can plug in X if you like that better, divided by T2, which is 55.9, but again, add 273 to that to get it into Kelvin. 328.9 is T2 then. So it's still just algebra. You just got a couple more numbers to multiply together to solve this, all right? It is still a fraction equal to a fraction, so I'm still going to cross multiply because that's just how I be. So this cross here then is going to be 0.987 times 25.5 times the 328.9. So on one of these sides, then we have 8277.92. I did round a little bit there. That's okay. will be equal to the other cross going this way now. So 301 times 1.04 times x. So that should be then 313.04 times x. And now I'll get x by itself by dividing both sides by the 313.04. $8277.92 divided by 313.04. We should get that x is equal to 26.4. And then the unit, well, we solved for V2 and V1 was in liters, so this is going to be liters. So the final volume after these changes is 26.4 liters. So overall then, did it go up or down? Yeah, it went up because 25.5 was the original and 26.4 is the final. So overall, the volume still increased, which means that the increase in temperature must have been carrying a little bit more weight than the decrease in pressure, okay? So there's all of our work for that one. Okay, that is all I have for you for these sets of notes. The worksheet that goes along with these notes is worksheet number 3 in your homework packet. Please be working on that. You know how to contact me if you need help. You can email me, you can Zoom with me. I'll make sure to help you with whatever you need. You are going to submit your final answers to a Google form for worksheet 3, and there is another video attached to show you how to submit your work there in case you're struggling with that, okay? So thanks for watching. This has been a great first episode of Chem with M. Bye.